All right, question 3, going in circles. So first let's go ahead and read the problem statement. Let U and V be two vertices on C sub n, which is the cycle on n vertices, and we want to find the probability that a random walk, starting at vertex U, visits every single other vertex before it gets to visiting vertex V. So first let's go ahead and visualize this. We've got this cycle, C sub n, and it's got, of course, n vertices, and we start at some vertex U, and the event we're looking at is the event of visiting all these vertices on a random walk, and the vertex that gets visited only after you visit all the other vertices is vertex V. And in relation to U, V can be anywhere on the cycle because we're looking at any two vertices, U and V. So V can be here. For all we know, V can even be right next to U. For illustration purposes, let's keep it over here. And let's just see an example of what a random walk might look like. We know we start at vertex U, and we have a 50-50 chance of going either to our left or to our right. So the first thing we do, of course, is mark vertex U as visited, and let's say I go to our right. Then from here, we have to visit this vertex, and I have a 50-50 chance of going back to U or going forward. Let's say I go back to U. And of course, the event we're looking at is that we keep doing this process of visiting vertices along the cycle, but we want to make sure that by the time we visit V, all the other vertices have to be visited. So in this case, we would have to go back. We're going back until we visit all these vertices that we missed at the start. And now that all the other vertices have been visited, we can go ahead and visit V last. So let's reset and give ourselves some notation. We are looking at the event that a random walk starting at vertex U visits every single vertex before visiting vertex V. So we can denote this by E sub UV. And the question is asking, what is the probability that E sub UV occurs? So this is our end goal, this is our answer. To make this easier on ourselves, we might want to number these vertices on the cycle 1 through n. And notice since it's a circle, it's completely symmetric, it doesn't really matter where we start our numbering of what starts off at 1, and then we might go around the circle, say clockwise, and number them 1 through n. So we might as well go ahead and make U numbered number 1. This makes it easier on ourselves since U is always fixed to 1. The only thing that's really varying then is V. So we can go ahead, number these, and we have to keep in mind that V isn't some fixed distance from our vertex 1. We don't know whether it's on the other end of the cycle. We don't know if it's really close. It might be right over here for all we know. So to kind of keep that in mind, I'm going to go ahead and rename the variable V to I, because I is normally a variable that we use for iterating. And I want us to keep in mind that I kind of iterates, it could be any one of these values. And now the new probability that we're trying to find after we go ahead and with this relabeling, renumber the whole cycle. The new probability that we're trying to find is the probability of E sub 1i. In other words, starting at vertex 1, what is the probability that a random walk visits all the other vertices before it visits vertex I for any I on the cycle? And for any I mean any I, 2, 3, all the way to n. It just can't be equal to 1 itself. A good thing to note is this kind of forms a partition. As you iterate over all the possible values of I, you go over every possible vertex that could be visited last. There must be some vertex that gets visited after all the other vertices has been visited. So if you sum over all of these probabilities, you get it equal to 1 because it's a partition. So that's one nice property we have. We might want to look for some other properties to help us in our process. So another thing you might notice is this nice symmetry that we have because it's a circle. To do a little example, if I started a walk at vertex 2, the event of me visiting all other vertices before I visit vertex 1 is basically the same as starting a walk at vertex 2 and visiting all other vertices before I visit vertex 3. You can kind of imagine this as taking your cycle and picking it up and flipping it back down. That it's completely symmetric, so it doesn't matter whether you go one to the left or one to the right. In math terms, we can write this as the probability of E sub j, j plus 1, is equal to the probability of E sub j, j minus 1, where this addition and subtraction is of course done mod n to preserve the cycle. Okay, let's go ahead and recap everything we just found. We defined the event we're looking at, and our goal is to find the probability of that event occurring. Then by renumbering and relabeling things, we found a nicer way to express that. We found out that this forms a partition, and we found this nice symmetric property. Since these two quantities are equal, let's go ahead and call the value that they're equal to s, just to give it a variable. With that all in mind, let's go back to our end goal is to find what is the probability of E sub 1i. Whenever you're trying to find the probability of some event occurring, a good strategy is to try and find a partition so that you can use the law of total probability to represent it in some way that might be simpler. So in this case, we can go ahead and look since we want to visit vertex I last, a good starting point might be to look at the vertices on either side of it. So notice that there's only two things that can happen. Either we visit vertex I minus 1 before we visit I plus 1, or we visit vertex I plus 1 before we visit I minus 1. So if we define these by two events, we form a partition. More explicitly, if f for first represents f sub I minus 1 is the event of visiting vertex I minus 1 before visiting vertex I plus 1, and then we have the symmetric event fi plus 1, which is the event of visiting vertex I plus 1 before we visit I minus 1. So these two form a partition because either one or the other has to happen, so they are disjoint and exhaustive. So in particular, we know that the sum of their probabilities must sum up to 1. So with this partition, we can express the probability we're looking for using the law of total probability as the probability of E sub 1i is equal to the probability of E sub 1i and this event occurring, plus the probability of E sub 1i and the other event occurring. And once we have this expression, we can go ahead and use some probability rules that we know. In particular, we're going to use the definition of conditional probability and represent this conjunction as this two on either side. So this is the probability of E sub 1i given f sub I minus 1 times the probability of f sub I minus 1 and symmetric on this side. Once we have this expression, let's analyze what these new events actually mean. So the probability that a random walk starts at vertex 1, visits all other vertices before it finally gets to vertex I, given that you visited vertex I minus 1 before you visited vertex I plus 1, we can kind of visualize this as I started at vertex 1, and I might have gone to the left first, might have gone to the right first, but I don't get to vertex I plus 1 until I go all the way around, hit vertex I minus 1 first, and then from here, I know I have to end up at vertex I, but I still haven't visited vertex I plus 1 yet. So that would look something like maybe having to go all the way around the cycle to finally get to I last. So because this is kind of a Markov memoryless process, it doesn't really matter the first things that we visited before we visited vertex I minus 1. So in other words, this event is equivalent to E sub I minus 1 I. And symmetrically on this side, we get E sub I plus 1 I. In English, this means starting at vertex I minus 1, doing a random walk, and visiting vertex I last. But notice that these two events are exactly the symmetric property that we noticed from before. So we can go ahead and replace both of these quantities with just s. And then if we go ahead and factor the s out, we get this. And these two properties are the ones that, these two probabilities are the ones that form a partition and sum up to 1. So this just becomes s times 1, which is of course s. Notice what we really discovered here. Even though we haven't quite figured out the value of s yet, we have proved something pretty important. The probability of doing a random walk starting from 1 and visiting all other vertices before you visit vertex I is completely independent of what I is itself. It doesn't matter where on the cycle I is. So that's a pretty important fact to keep in mind, and combined with the other facts we have, we can just put this together. And notice that this summation, we can go ahead and replace the same quantity throughout, and just get that s is equal to 1 over n minus 1, which is exactly the probability we're looking for. So the answer here is n minus 1. More intuitively, all this math is saying is that since each one of these probabilities is equal to the same value, regardless of what I is, and we know that they all sum up to 1, all n minus 1 probabilities here sum up to 1, each individual probability must be 1 over n minus 1. And there's n minus 1 of them because we start our numbering at 2 to go all the way around for all possible values of I. So our final answer then is 1 over n minus 1.